Alrighty, welcome back to APS105. So today we get to talk about the exciting world of structures, which is a way in C to help, well, as the name implies, structure your code, and specifically data. So what we can do is you can group variables within something called a structure. So this is another instance where you can create your own type, like what we talked about before with enums, but now you can actually have different variables all grouped together. Enums you probably will not use. Structs we will use extensively, so this is one topic you should definitely know. So the syntax to declare a structure is struct. Again, we have to make things short. Struct is a keyword, so you're not allowed to name a variable struct or anything like that. So you type struct, you give it a name, and then in a set of curly brackets ended by a semicolon, you can declare a whole bunch of variables, and they'll be your normal variable declarations, type, name, semicolon. So you can add as many variable declarations as you wish. So when you add one of these, you should define the struct just below the includes and not within a function. So how we would do that, let's take, for example, this little program that calculates the distance between 2 points. So right now, what you know, you would have to create, in this case, if I have 2 points, each with an x and a y, you would have to create 4 variables and then handle the naming yourself. So I might choose to creatively call the first point, point 1, and I'll say it has an x1 and a y1. So that would be the coordinates of the first point, 1 and then 2. And then for the second point, I could have x2 and y2 as 4 and 6. And then if I want to write a function to calculate the distance between these 2 points, well, I have to put in my argument list all 4 of them. So I have double x1, double y1, double x2, double y2. And then, as we know, to calculate the distance between them, it's just the square root of the differences between them squared. So in C, it would just be squirt, or square root. And then, as the first argument, it would be pow x2 minus x1. So the difference between them to the power of 2, so squared. And then plus the differences between the y's again to the power squared. So we could use our program like this. This is what we know right now, but we can make this a bit better and a little less error prone, because as you might imagine, these names are pretty terrible. Keeping them straight might be difficult. You might screw them up. You might get them in the wrong order. You might do like x1, x2, y1, y2, or something like that, which would give you, of course, the wrong result. So it's not that bad to remember which variable is which if you're not using multiple points. So if I write a function like print double xy to represent my point, and in the declaration I just print out the line point and then the coordinates in parentheses, I could do this. It's a bit awkward to use again because, well, slightly less arguments to confuse between, but I might accidentally write something like 2 unrelated points altogether, x1 and y2. So this wouldn't be that great, especially if I intend to print off one of those points and not half from the x coordinate from one point and the y coordinate from the other point. So what I can do is I can make a structure that represents a point, right? Logically, I should group together x and y into the same structure. So a struct kind of just groups things together, how you can think of it. So I can make a structure that represents a point. You give it a good name, so I'd call it struct point, and then curly brackets, I say it has a double x and then a double y. So like with the enum thing, this creates a new type called struct space point. And because it's just a type, I can create a new variable with it using struct space point. Then I can create a point called p1. So to access these fields or members, usually called fields or members, or just access these inner variables, whatever you want to refer to them as, you can access them with just a dot. So for example, whoops, if I want to access x in the point P1, I can do P1.x. And if I want to access the x or y coordinate, I can do P1.y. So those are both now grouped together in P1. So it's much harder to confuse the x and y, especially when we use this to modify our functions as well. Also, remember, slight little trick people do is you can rename types with that typedef thing again. So the syntax of a typedef again is you can typedef some type to refer to it by a new name instead. So you can use this to shorten struct. So if I don't want to write struct point, I can do something like struct_t, or I can just not give a name to the struct itself. A whole bunch of different options that we will go into. So again, we use the typedef to save us from writing struct everywhere. So you're able to create a struct without giving it a name, similar to what we saw with enums before. So I could do something like typedef struct and then curly brackets $x $y. So this is a type. It's a struct without a name. And then I say, let me refer to this struct without a name as point_t. And then afterwards, it looks a bit nicer. It doesn't have a space in our type. So I can create a variable with point_t p1. Usually with this, unlike enums, you still give the struct a name just in case. So you say typedef struct point, curly brackets, then x and y, and you say, oh, I can also refer to this as point_t, but you also have the option to refer to it as just struct point if you want. Then it's kind of just up to a style thing, what you prefer. They both mean the same thing. Yep.
So point TP1 and point P1 would be the same.
Point, sorry?
Like if I said point TP1, and then underneath that I said point P1.
So,
Yeah.
yeah.
And then I said point P1, it would be the same thing.
Oh, if you said point P1, no, you'd have to say struct point P1. So yeah, struct point P1, because the name point by itself doesn't refer to its type. It has to be struct point. So like we saw here, it would have to be like this, struct point P1. So now I can create them. If I use this syntax, or if I use this line here, or this typedef, I can either do struct point P1 or point_p P1. Generally, you'd prefer this one because it's a bit shorter and it gets a bit more to the point. So using this, I can create our 2 points and then initialize the fields or inner variables or however you want to call them. So I can create a point called P1, and then it looks a bit more clear what I'm doing. I can do P1.x equals 1, P1.y equals 2, and then point P2, P2.x equals 4, P2.y equals 6. Looks a bit clearer, but I can do better. So I can actually initialize structures like arrays if I want to do it all in one line. So instead, I can just do point_t P1 equals, and then curly brackets around it, just like the array initializer. And then it will assign the values in the same order as you declare the fields or declare the variables in the struct. So this will set x, since it is the first one in my struct, to 1, and then y to 2, and then similar for the other point. So now this looks a lot clearer. So this, again, always sets them in the order in the structures. If for whatever reasons I wanted to set the values in a different order than they are in the struct, I can specify which field I want to actually initialize with what value by using .x or .y equals some actual value. So if for whatever reason I wanted to declare the value of y first, I could just do .y equals 2 and then .x equals 1. It will give us the exact same thing as this. Yep.
Why is there a comma after the .x equals 1?
Oh, the question is, why is there a comma after this x equals 1? And that's just a style thing I do. This comma does not need to be there. But I like having that comma because if I swap the lines around, I don't have to remember that, I have to remove the comma from the last line and things like that. So valid way to do it in C, just makes it easier to swap around. Yeah, I absolutely do not need this comma. All right, so if I wanted to, I could rewrite that whole example now using a struct instead. So that big double thing, I could write type-def-struct point. It's an x and a y. Now I can rewrite distance. So in distance, instead of taking an x1 and a y1 and an x2 and a y2, I can now take a point p1 and point p2. And now it's a bit clearer in here that I'm taking the difference between 0.1 x's, and I can't screw them up because they have to come from different points. And then here I go ahead and I do the difference between the y coordinates between these 2 points. So even reading the function definition, it is, I'll make some more space. It's a bit more readable because you can actually tell which coordinate is from what point other than just coming up with your own naming scheme and just hoping for the best. And I can also modify my print function. So print, I can just take a single point as an argument. So same rules still apply. They're all copied by value. So the entire struct gets copied. This function gets a new copy of all of the values of that struct. I imagine could be very big or copy a lot of memory, but in this case, let's not care about that for now. We will get to it. So I could write my print to just use x and y from a point, and now when I declare everything, my function can be a whole lot shorter. So I can declare my 2 points. Very evident from reading this, which coordinates correspond to which points. Oh, this one's a lot more readable too. I'm calculating the distance between point 1 and point 2, and then after, well, I don't use the print function here, but I could. So if I go ahead, compile this, oops, where are we? We are at lecture 27, compile. So if we go ahead and run this, we'll see that it does the exact same thing, point distance. So we'll get 5 between our points. That's what we expect as our result. So we went from this ugly main that had a whole bunch of unstructured numbers and then took them in an error-prone way in a very certain order, and we changed that, rewrote everything to use structs, and then we ended up with this. So a lot clearer to tell which coordinates correspond to which point, a lot clearer to read the functions to, a lot less error prone. So any questions about that? Yep.
So is this struct like any faster than the original program, or is it just to enhance the readability?
Yeah, so the question is this struct any faster than the original version? The answer to that is no. It's not any faster, it's not any different, it's just a lot easier to read and organize, especially as your programs start getting bigger. Yep.
So does this struct, like, I'm assuming it has its own pointer, right? You could have a struct pointer. Right?
Yep, you could have a struct pointer, yep.
Is it also 8 bytes?
Yeah, all pointers are 8 bytes, yep. I think you were first, yep.
Yeah, so like actually for this function distance, would it be faster or slower than the original one? Like, would indexing the values in the struct points contribute to it being slower, or?
No, the indexing, by the time it hits the compiler, or by the time the compiler compiles your code, that all goes away. Yeah, so this would be exactly equivalent from before. Just we group together, this is a group together of 2 doubles, this is a group together of 2 doubles, and before we had like 4 doubles, right? But it's going to do the exact same thing. The compiler is going to do the same thing. It's not going to be any faster or slower. Yep.
So when we call it into a function, do they make a whole copy of the points? Or is there all new points, or do they just copy the x and the y?
So it would, in this case, create a whole new copy of that point with all the fields. So in this case, like here, this would create a new copy. So you just pass by copy. So this would be a new point with a new x and a new y. That's a copy of whatever it was before. Yeah.
Would there be any extra memory that's needed to define the structure?
Yeah, the question is there any extra memory that's needed to define a structure? If the types are all the same, no. If you mix types, so you're allowed to mix types here. If you're allowed to mix types, the compiler has a whole bunch of rules to how they're spaced out, which are the same rules to space them out anyways. You don't need to know those rules. We can just ignore them for now. But there might be some very subtle differences that you won't care about until 4th year. So, yeah, so it would be copied by value. So in this case, it would copy 2 doubles for each of them. So it would be 4 doubles copied in this function. Exact same thing as we had before where there were 4 doubles copied in this function. The only drawback would be, hey, if I create more fields here, so let's say I put a Z, then it's going to copy all of those variables whenever I pass by value there, which again is what C is. All right, any other questions before we move on and touch on pointers, which is the fun one? All right, cool. So, like I said, function arguments in C are copied by value. Sometimes structures, especially as you have a very complicated program, get very large, and copying them may be slow. So, just like variables, you can't modify the values in the caller. If I wanted to go ahead and modify, I don't know, the y coordinate in one of those functions, I couldn't do it because I got a copy of that point. Any changes I make to it will only persist in that function. So normally, because of this and because of the rules, normally programmers always use structure arguments as pointers so they can actually change the values of the struct, just like we had before. So I would actually probably write this function as double distance point underscore a point t and then a pointer to it, and then a point t and then a pointer to it. So again, we don't really care about performance, but this is going to be slightly slower than the version we had before in this case because we also have to create a pointer as well as storing the double values themselves. But again, we are not worrying about optimizing our code or anything like that. First and foremost, we are trying to make it correct. So there's an operator to help you access fields through a pointer. So assuming I have the variable p1, which is a pointer to this point underscore t, if I want to access the fields, we have to do dereferencing, right? So if it's a pointer, I have to do star p1. That gives me the actual value of the structure. And then I'm allowed to do .x. So in this case, if I get it by a pointer, I always have to dereference it to get a point underscore t, because remember, dereferencing basically just removes one of these stars. So I would get point underscore t, and then I can actually access x. But like we don't like doing dereferencing, we don't like doing pointer arithmetic or anything like that, there is some help C gives you, or a different operator that is equivalent to doing the dereferencing, but is a bit more readable. So there is an operator that people just call the arrow. So it's minus greater than. So it won't actually do a minus or greater than. That's supposed to represent an arrow. That's the best we can do with just characters on our keyboard. So this is an arrow operator that combines dereferencing and field access. So instead of writing, and I would have to write the parentheses here because of the precedence rules, and it kind of gets annoying to write all the time. So instead of doing parentheses, dereference p1, and then, oh, okay, now I can access .x, I can just use this arrow operator. So the p1 arrow x is exactly equivalent to this. So it allows me to access a field through a pointer instead, and this will do this arrow will do the dereferencing for you. Bit nicer way to go ahead and access our variables. So we'll probably end up using this. So if I wanted to change the function to use pointers, so this is generally what happens. We'll see, let's check what the compiler warning is. So let's say I just change these to pointers. So if I just change these to pointers and try and compile it, I can already see some angry red underlines, and it says error passing point underscore t, aka struct point. So our compiler, hey, it knows we type defed it. So see 2 ways to refer to it. Then 2 parameter of incompatible type p1, aka struct, a pointer to the struct. And it says, oh, you should probably take the address with the ampersand. So if I go to line 21, I can see, oh, well, my function is using pointers now, so I have to give it a pointer in both cases. So I'd have to do, whoops, look at the correct monitor. So I have to do ampersand p1 and ampersand p2. And then, as you might do, you might be like, hey, okay, I fixed that, let's compile again. Oh, we got another error. So it says member reference, which is a field or inner variable, whatever you want to call it, of type pointer to point underscore t, aka a pointer to the struct point, is a pointer. Did you mean to use the little arrow operation? So it's even telling me, hey, instead of this period, you should just use the arrow operator. So I can go through, change it all. This is the only change you would typically make. Generally, this is something you just get into without the compiler's help whenever you first make a function, but you might need the compiler to help you the first few times. So now I can compile this, I can run it, behaves the exact same way as before, but now I get a copy of a pointer whenever I call this function instead of copying a struct. So if I add more fields, so if I do double, x, maybe I'd give it, a name, something like that. It means I'm not copying all of those fields whenever I create a new point, or whenever I call a function. I'm only giving it the address, letting it copy the address of the variable again and again and again, instead of wasting a lot of memory copying every single field of that struct. So questions about that? All right, so we changed the function to use pointers instead. And so you have it on the slides. Again, you can't access a field using period with a pointer. Again, we'll get this compiler error message. It's easy to fix, but like I said, if you're mixing them, it's a common message you may see. Yep.
Can you go back to the code?
Yep.
So when you have care name, right?
Yep.
The array. So if I said like p1 arrow name,
Yeah.
is that returns the first element?
Yeah. So p1 arrow name,
Yeah.
that would give you the array type back, right? Which would decay to a pointer.
And then I can just do pointer with the array, right?
Yeah, or you could just treat it or make it a C string or whatever you want.
Oh, okay.
Yeah. Alrighty, so All right, so following is more advanced C programming. You may not be able to use them all for the course, but we'll go over to a few things. Everything before this, you'll definitely need to know. Everything after this will just kind of help you organize things a bit better and make your code a bit more readable and kind of understand what's going on, because in the recent labs, you also have header files and things like that. So, whoops. So, what we can do, whoops. So, other things we can do, we can create a structure dynamically. So usually we use our own dedicated function for this. Oh, sorry, this is still included in scope. So I might do something like create a function called pointCreate, because if I'm doing it by pointer, well, probably I just want a whole bunch of pointers back, and I just want to use everything as a pointer. So I can make my own function called pointCreate that takes the initial values as an x and a y, and then internally it's going to return back a pointer to that point_t. So it's something we have to malloc, right? We can't just create a point on our stack and return an address to that because the variable will not exist anymore. So we have to use our handy dandy malloc function. So in it, I could just malloc the size of a point. So that will malloc enough space to hold that entire structure on the heap, give us back a pointer that we can use for it. And then here we can initialize the fields by just using the arrow operator and then return point, which is whatever we got back from malloc. So this lets you kind of have that niceness of that initializer with actually allocating a point dynamically, and you can initialize it in one step. So now I can say point_t and a pointer to that. So there's a star, p1 equals point create 1 and 2. So because I'm using malloc again, we have to be good programmers, and now we also have to remember to free p1 after we are done with it. So usually you prefix all of the functions that use that structure with the name of the structure. So in the case of this point, all of our functions, just by a style kind of guideline, should start with point and then an underscore. So we should define our other functions, if we rewrote them this way, as point_distance, that takes 2 points by pointer, and then point print, which will print off that point, and we will change it to use a pointer. Just for consistency, make everything a pointer. So now we can use point, and we're just accessing the fields by itself. Everyone still good? Still pointers? So this is the beginning of stuff you don't really need to know, but again, lab 6 and 7 use this. So what you might want to do is, hey, I'm getting a lot of code. I don't want to throw all of my code in the same .c file. That is lame. So maybe to break apart my code into smaller pieces, I create a file called point.c that contains the definitions of all my functions that start with point and then an underscore. So I would put my definitions of point create, point distance, and point print in there. And then, well, turns out that point.c could also be the only file that defines the struct itself. We'll see a bit more on this later. Then we can create a file called point.h. So that's a header file that should have all the declarations of functions we are going to define and that we are allowed to use in our program. So that will contain all the function prototypes. Then I can use them, all these functions, in other C files. So they don't all have to be in one C file. So again, we call the .h file a header file, mainly because it's supposed to come before your code. So it's supposed to come at the top, aka a header. So this is what a common header file would look like. Again, in this course, you don't really have to create your own, but this is what a common one would look like. So it would have this weird thing at the top that says if ndef point.h. So in the C preprocessor, it defines its own variables and things like that. This file could be included from multiple C files or multiple header files as well. There could be a whole chain of them. So if you actually declare the same function twice, C will give you an error. So we add a bit of code to this so that this code will only get copy and pasted into our .c file actually once. So it checks to see if a variable called point_h is defined. Generally, you call this kind of variable the same name as your file. And then if it's not defined, it goes in here because this is an if statement. So it defines the variable point_h. So now that variable actually exists. We kind of use it as just a Boolean. And then if this is the first time encountering this, it will do the type def struct point_t. And if I don't have any curly brackets or anything like this, it's something called a forward declaration. So you're saying, hey, see, there's going to be something called a struct point. It will be a structure. I will not tell you whatever fields are in it. Just know that it exists. So you don't have to be concerned about it unless you try and access fields or try and access the X and the Y. So I could do something like this, and then Well, because I use a point_t by pointer, I don't actually care what the fields are. So in these functions, I can just return a pointer to point_t, and then in point distance and point print, I just go ahead and use all the arguments by pointer. So, like I just explained, that header file is included only once, and it also hides the definition of that struct. So anything that starts with a hashtag is a preprocessor command, so it's before the compiler actually runs. So that just makes sure that if ndef and the define and the endif, just make sure that we only read this file once when we compile a file. So the other thing we did is we did a forward declaration of struct. So we tell the compiler basically, we'll define this later. You don't need to worry about the details for now. Just know that it exists, so I want to use it. So now I can create pointers to the struct. I don't need to know their fields. A pointer is just an address. I don't care. So now I can clean up my program quite a lot. So if I move all of, if I move point create and point distance and point print to a different C file, this could be my main C file that I compile into my program, and this would be it in its entirety. So in here, I can just include point.h, so this is the header file I have written now. Remember, whenever we do a hashtag include, the C preprocessor basically just copy and paste the contents of the file. So this point.h will get replaced by all the declarations I had before. So I'm allowed to use point create, point distance, and everything like that. So my main program now, I've separated it out like how I operate on points and what I want to do with points. So now I could just create 2 points. So I could point create P1 or point create P1, then print it out, point create P2, print it out, and then print off the distance between the 2 points, all in one file. And then when I'm done with them, of course, I have to free them. Yeah.
I'm just a bit confused. So with point.h, you just wrote the headers of the functions.
Yeah, so point.h, it would be just that.
So where's the actual implementation of the function?
Yeah, so the actual implementation would be like we'd have to create our own file. Let's see. So we'd have to create our own, like a different C file that contains all the definitions and stuff. So I'd probably put them in like a file here called point.c.
So in point.c, you include just the definition
Yeah,
of functions.
yeah. So
Only then can you just like simply write the function in your main program.
yeah, yeah. So here is my point.c file. So point.c can just include point.h, and then in it is what I had before. So I declared the structure in point.c, and then I can go ahead, define point create, define point distance, and then in this I added a whole bunch of other functions, which I'll get into in a bit, but this is our whole main function. So my whole main function is just this now. So when I compile it, I also have to tell the compiler that, hey, in the final executable, I need you to compile both point.c and main.c together to create the executable. Yeah.
So, like, was it, like, for point.c, you also had to include the header file, and then, like, how does it know that for main, you have to read to point.c, and it's not like point.c is reading whatever.
So the question is basically,
Like, at the top, it's kind of the same, right? Like, you're just including the header file.
yeah, so at the top I'm including the same header file. In this case, I probably don't need it. So if I wanted to, I could just go ahead and remove it. It doesn't actually matter because I'm declaring all these functions here. So I don't actually need to include point.h and point.c. It doesn't really matter. It's kind of more of a style thing. And sometimes, in this case, I'm not using any crazy types or anything like that. But if you used some weird combination of types, you'd want to use them in, like you want people to use them in other C files, and then you should also use them in your C file. So typically, you always put them in. It just has all the declarations and everything.
How does point.h know to go to point.c?
How does point.h know to go to point.c? So point.h doesn't care about point.c at all, right? So when I compile my programs, I only compile .c files. So if I if I compile this .c file, it will contain code for like point create, point distance, and everything like that. This point.h file essentially would just get copy pasted here, right? So if I comment it out, it means that I won't get all the declarations at the top of my point.c, but it doesn't matter, right? Because I'm defining the functions here. I don't need to put the declarations on top unless, I tried to use it before I declared it or defined it or anything like that. So that's why I don't need it for this. And the other step is when I compile it. So when I compile it, my compiler has to compile both main.c and point.c, and it'll combine them together in your executable. So yeah, that's something the compiler will do for you. So it just needs them all to be thrown together in something called a linking step. So if, for instance, this point create wasn't defined anywhere, you would get an error after your code compiles that like, hey, I couldn't find point create. So we can actually do that. So let's see what the error is. Again, this is why you're doing it in a single C file, because this gets into more like, other steps of compilations. So if I do that, you might notice this error when you forgot to include the math library. So it gives me a whole bunch of kind of garbage. It just says failed to compile main, failed to compile main.c. And you can see here, compiled everything, and then it said error in function main, some random thing here, undefined reference to point create. So it's saying, hey, you used a function called point create, but I don't have its definition anywhere. I don't know what code to actually call. And you'll get something called a linker command failed with exit code 1. So linking is the word we use when we combine two C files together. So this is why we tell you to do everything in one C file for the lab, so you don't have this linking thing. But as you saw with not including the math library gets linked in so you can use the math functions like square root and all that. Yeah?
So technically you don't need point.h, right? You can just have all your declarations and implementations in point.c and then just link the two.
So the question is, well, does that mean I don't need point.h? And the answer to that is, well, I need it for when I want to actually use that, right? So if I removed it here in main, you can see all the red that came up because now it doesn't know what the hell point create is or anything like that. It needs the declarations of the functions to know what the inputs and what the outputs are, right?
Yeah.
So the point.h is needed. It's generally always needed whenever you try to use the functions. It might not be needed whenever you are defining the functions. So if I do this and compile this now, it'll complain at me a lot, but it'll be like, hey, I don't know what the hell a point_t is. Hey, I don't know therefore I don't know what P1 is. Hey, I don't know what the hell point create is, everything like that. So if I include point.h, then it'll essentially copy and paste all of this in. So I'll have all the declarations of all my functions there. So now C actually knows about everything that I defined. All right, cool. So and also this kind of gets Java, but we'll ignore that for now. So now, oh yeah.
Wait, so what is the command specifically for linking?
What is the command specifically for linking? So if you want to just simply link all the files, I believe if you want to do it by hand, I haven't done by hand in a while, you can just specify main.c and point.c, like both together, and this will compile and link them all in a single step. So if I do something like this and do, I don't know, test, Oh, I need to add the library or the math library. So if I do this, I can do them all in a single step. This will compile and link them all together in a single step. Because if I just try and compile, I don't know, main.c by itself, I'll get some error. Oh, it'll try and link itself and try and find point print and point create, and then it'll just complain at me the whole time. So,
Like similar for GCC.
sorry?
It's similar for GCC.
Yeah, same things you type for GCC, just replace Clang by GCC. So this is the way to do it by hand. You might notice this like meson.build file in your lab thing. So you can actually, it will do the correct thing and compile them separately if you do them here. So for example, in my main program that uses them both, I can say, hey, create an executable called main. The sources are main.c and point.c, and it also needs a math library. So this is how most developers will do this, and then they'll just add more C files as there are more C files they need. Because compiling it by hand is kind of silly. All right, so other thing we might need to note, let's see. So we've screwed this up horrendously. So now we might notice that because we forward declared everything, I can't do something like p1.x anymore. So if I do the arrow x, I get the little red squiggly line again. If I compile it, let's hide this. If I compile it again to see what the error message is, it says incomplete definition of the type struct point. Because here, like I said, there's a forward declaration of struct point. In point.h, I don't actually say what the fields are or anything like that. So I can't actually access the fields in the function itself. If I want to keep it that I can't actually directly access the field, so there's some good reasons to disallow people to do that, some good ones to allow them to do that. But if I wanted to make sure that they can't actually access the fields directly themselves, well, I'll keep it as is. I'll forward declare it, hide the details. It's a bit more flexible that way for, again, reasons you won't get into until like third year. So what you need to do in this case is create more functions to access and set the values, which might be familiar to you if you used a programming language like Java or anything like that, because in Java, everything's a pointer. They just don't tell you about it. So typically, you create a getter function to get the current value of a field, and a setter function to modify the value of a field. So this will, again, common if you are a Java programmer. So I could create some more functions here to actually, oops, where's my mouse pointer? I can create some more functions here to get the value of x. So I take a point by pointer, so pointer to point underscore t, and the return value is a double. So I'm just going to return a copy of the value of the current x coordinate. And then for set x, well, I take, in this case, a pointer to the argument p. So in Java, you typically write like this. This is basically a pointer. And then this is the value I want to set the field to, and then its return value is void because, well, it doesn't have to return anything. And then I could do the same thing for the y field as well. So that's our complete header file. It doesn't know the definition of the struct. It's more flexible for software engineering reasons if we can actually hide the details, because we could actually change things without breaking a whole bunch of code for subtle reasons. So this was what we had at the start. Our point.c, just so you have it all in a single slide. Again, you have access to the repository. I don't actually need this include.point or this include point.h here. So in point.c, which has all of the declarations of my point functions, I have to declare the struct itself because I'm going to be accessing the fields in this .c file and only as this .c file. So for point create, I'll have what I had before, which will malloc it. and then distance, what we had before. Now get x, all that will simply do is return p arrow x, because I'm the only thing that's allowed to know about the field x, so I'll return the current value of x. And then with set x, again, it's just an assignment that makes it equal to the value passed in by an argument. Same with the y coordinates, and then same with print. So that is the totality of our point.c code. So when we compile, we need to use both files, right? So we need to, in this case, I put the main function in a file named main.c. So if you have a lot of C files, you broke your program into a lot of different files. It's really easy to find where the main function is. It's in the file called main.c. And then to compile both of them at the same time, like I showed you, you could, if you prefer GCC, you could do GCC point.c, or main.c, and then the name of the executable you want. In this case, I use the math library, so I have to use -lm. So afterwards, I can just run main as before. So if I have this now, I delete it, I compile and run it. Again, this is my entire main. If I run it now, I can see that, hey, it actually does kind of what I expected it to. I printed 0.1, I got 0.12, printed 0.2, I got 0.46, and then the distance between them is just 5. So just a different way to structure your code. And again, I had to free them as well, just so I didn't have any memory leaks or anything like that. So having multiple C files, again, beyond the scope of this course for whatever reason, but as you write bigger and bigger programs, you will definitely want to do this. So, any other last minute questions before we get released? All right, you are henceforth released. I don't know why I said it like that, but remember, I'm pulling for you. We're all in this together.